Although we've already seen how to apply boundary conditions to solve problems in heat transfer, we're going to take a moment now to formalize that knowledge and in the process, introduce a new type of boundary condition. So far, we looked at just specifying the surface temperature. This is giving an explicit value of the function at the boundary. So imagine we have a temperature distribution T of x, and at the interface at x equals 0, we say that we have a temperature of T sub s. Mathematically, we're saying that T at x equals 0 equals T sub s. You might be wondering how we would ever even maintain a constant surface temperature. One could achieve this using, for instance, a control system. In this control system, one would have, for instance, an IR thermometer, like this. Use that to measure a surface temperature. And if that surface temperature is higher or lower than the desired set point, change the amount of heat that is introduced in the system to reach that desired set point and keep the temperature at that surface temperature set point. One could also introduce a phase change in the system, for instance, water boiling. This is a great way to maintain the system at a temperature of 100 degrees centigrade. We can also instead specify a surface heat flux. This is a case in which the first derivative of the function is specified at the boundary. So if we have an interface of the sort shown here, we can specify at this interface that q sub s double prime is of a particular value. Mathematically, this means that we have minus k dt dx at x equals 0 equal to q sub s double prime. So this is just Fourier's law applied at the boundary in a case where we know the value of the heat flux. If we have the special case of an insulated boundary, this means that the heat flux is 0. There is no heat crossing that boundary. We could also in our system have a point of symmetry. Points of symmetry also generate no flux conditions, where q sub s double prime is 0. This is a case that we will explore more in other problems that we work. Imagine we have a system in which a window pane is in contact with air. The window pane has conduction of heat through it, while the air is convecting. We're interested in finding the temperature distribution, T of x in the window, so we need a boundary condition at x equals 0. If we know neither T sub s, the explicit value of the temperature, or Qs double prime, the heat flux at the interface, then we need a way of creating a boundary condition at x equals 0 that accounts for the fact that there is convection of air at this interface. So we can try then to apply Fourier's law at this interface on the air side. Let's say that we have Q double prime convective equal to minus K times Ts minus T infinity in the numerator and this length scale L in the denominator. Here, K is for the air, and L would have to be a length scale on the air side as well, the length scale over which we go from T sub s to T sub infinity. But of course, L is something that we don't really know. We don't know how much distance we have to traverse from the interface into the air to reach the bulk temperature T sub infinity. Similarly, we also have trouble with the value K. The thermal conductivity in air can be hard to pin down because the air can have a whole distribution of velocities at the interface. This gas is moving around, it is stagnant at the interface, it has a velocity further away from the interface, and accounting for this velocity distribution to find K sub x as a function of distance is difficult. So we can instead choose to lump K and L together into one parameter h. We define then this quantity h, and we have Q double prime convective equals h times the quantity of T infinity minus T sub s. All we've done here is combine K divided by L into one parameter h, and we've absorbed the negative sign into the expression in the parentheses. We refer to this expression Overall, Q double prime convective equals H times T infinity minus T sub S as Newton's law of cooling, which we apply to convective heat transfer at an interface. We can take a moment now to define what the heat transfer coefficient is, this quantity H. It has units of watts per meter squared per Kelvin, which we can glean just by seeing that we have a ratio of K, the thermal conductivity, and a length scale L. H depends, for instance, on the fluid velocity. It depends on how quickly air is moving past this window. If the air is moving more quickly, H has a larger value. If the air is moving more slowly, H will have a smaller value. And for similar reasons, it depends on the viscosity of the air, the density, the geometry that we're in. All these factors play a role in terms of determining the value of H. It's also larger for forced convection than for natural convection, since we tend to have a higher velocity with forced convection, and it'll be greater for liquids and gases due to the frequency of collisions between molecules in liquids versus gases. So the boundary condition then is Q double prime conductive equals Q double prime convective, that the heat flux for conduction in the window must be equal to the heat flux for convection in the air. And this means then that we have minus K dt dx at x equals 0, the flux due to conduction in the window, equal to H times the quantity T infinity minus T sub S. This is the heat flux from Newton's law of cooling, which describes convective heat transfer.